Hi everyone, good afternoon. So today I'm going to talk about quantum algorithms for solving semi-definite programs. And this is a joint work with Joran van Apeldoorn, Fernando Brandao, Anur Shkilian, Amir Khalif, Cedric Yan-Yulin, Krista Swar, and also Xiaodei Wu. So can the people at the back hear me? Oh, great. Okay, so the first thing that I want to do is that I want to give you some motivations for studying this topic. Maybe a very first example here is a problem like this, which is basically a supply and demand problem. So for this problem, we are going to make the delivery from some supply stations to some demand stations. And for the delivery from one supply station to one demand station, you are going to gain some money per unit. For this problem, you are going to have two restrictions. So for the demand side, you are going to make have the restriction such that all the demand stations should really be fulfilled. And also on the other hand, have this kind of upper bounds on the supply side, such that you really really the upper bound you can provide the total amount with. So I think this kind of problems very naturally appear in real applications, and in particular, people really want to maximize the total profit that we can gain from the problem. So how should we model this problem? So here, maybe we can denote some variables. So here we denote xi to be amount that P1 sends to Ci. That is basically, this is x1, x2, and x3 respectively. And similarly, we denote some y1, y2, and y3 respectively. So basically, the problem of maximizing the total profit of this supply and demand problem can be characterized by this optimization problem, where basically you want to maximize this function, and also we have the subtractions here. So basically the first three inequalities here are basically for the constraints on the demand side, and also these two inequalities are basically the requirements for the supply side. And also, of course, for this kind of problem, we should have the restrictions such that all the amounts here are non-negative values. So basically, I think I just want to give you a very real application such that basically we have a very natural optimization problem that we want to study with. But if you're kind of familiar with optimization theory, this kind of problem just belongs into the categories of a linear program, where basically we want to maximize a function which is linear, and also the subtractions here are also linear inequalities. And also here we have variables here to be non-negative variables. So this is the problem of linear programming that I guess probably most of you have been familiar with. And today I'm going to talk about a slightly general class of problems, the semi-definite programs. So you see that this kind of, these two problems are really similar in their form. So in particular, I would like intuitively saying that LP is just like a scalar version of the SDP problem. So in particular, for both the problem, we are going to denote M to be the total number of constraints. But for the SDP problem, instead of having some scalars x1 to xn, we are going to have a variable matrix X, which is an n by n Hermitian matrix. And also on the other hand, we are given a promise specifically for the SDP problem that X is a positive semi-definite matrix. That is to say, all the eigenvalues of X are non-negative. So you can see that this is really like a scaled up version or a matrix version for the problem where we consider PSD matrices. And also for the special case of LP, it suffices to take the matrix, target matrix C here to be a diagonal matrix, and also the constraint, all the constraint matrices AI here to be diagonal matrices, so they're just reduced to the LP case. But in general, for our work, we basically gave a quantum algorithm can solve the general SDP problem, which I will focus on in the rest of my talk. Okay, so first, beyond like a general real applications that I just mentioned, like this demand and supply problem, why do we want to study SDP? I just want to point out that this problem is a central topic in computer science. For instance, it has wide applications in machine learning because for machine learning, to train a model is just equivalent to optimize a certain loss function. And also specifically for the SDP, it is also very useful on the algorithm design side. That is, it can be used to give good approximation algorithms for max-cut, constraint satisfaction problem, the CSP problem, etc. So for this talk, I'm focused more on the algorithmic side. That is, I'm going to give a better understanding about quantum algorithms for solving SDPs. Okay, so let's delve into the topic. So let me just quickly recap what is the problem that we want to study with. So in this talk, I'm going to study with the problem where we have M constraints here. And here, all the matrices here, the AI, the C, the AI, we call them constraint matrices. The C, we call it target matrix. And here, the X, we call it a variable matrix. They are all n by n Hermitian matrices. And specifically to characterize the complexity of the problem, we assume all these matrices, all the matrices A, I, and C to be sparse, to be S-sparse. So here, we call the matrix to be S-sparse if every row or column of this matrix has at most S non-zero number of elements. And of course, a very important thing that we should restrict for the SDP problem is that the variable matrix X here should be a positive matrix, a positive semi-definite matrix. So as I just mentioned, like it has real applications like this kind of demand and supply problem, and also have that applications in machine learning and algorithm design. So people must realizing this kind of application, it must be also, on the other hand, we need to have some efficient solvers for the SDP. And actually, luckily, this is the case. There are some extensive literatures on studying the time efficiency of some SDPs. And in particular, there are two kinds of state-of-the-art classical algorithms of some SDPs with precision epsilon. So here, by the precision epsilon, I mean that you can return the maximum value within plus or minus epsilon, which is just like an additive relationship here. So the first kind of method is basically this kind of cutting plane method, which is quite similar to the more famous ellipsoid method that can basically get this kind of a complexity dependence. So here, instead of using the error dependence epsilon here, I'm going to make a rescaling of the problem. So here, throughout the talk, I'm going to denote gamma to be the error dependence, which is equals to capital R times small r over epsilon, where the capital R and the small r here are respectively the upper bounds on the primal and the dual problems of the SDP. So you see, it's just like we are going to get a correct scaling for the problem. So the good thing for the cutting plane method is that it is really error insensitive, that the dependence on the error here is small. But unfortunately, the dependence on the number of constraints M is cubic. And also the dimension dependence here is somewhat large. We have this kind of 2.373 dependence, which is just the constant for matrix multiplication. So this is somewhat large. Maybe if you want to consider applications in optimization or machine learning, this kind of things is really for big data applications might be a little bit too costly. And on the other hand, there is another kind of algorithm, and in general, it's like an algorithmic framework called the matrix multiplicative weight framework that can solve the SDPs in this complexity, which is actually trilinear in M and S, but unfortunately, the error dependence here is somewhat larger. So it's just like this is just like a quick message about the time efficiency on the classical side. And here we are at QIP. And a very natural question for us to ask is, can we give quantum algorithm that solve SDPs faster than the classical counterparts I just mentioned? I would say that maybe I just asked a random, a person in our field, maybe the answer could be yes, because I think at the very beginning I mentioned this kind of demand and supply problem, which is a linear programming. But on the other hand, linear programming is a generalization of linear equations, which can be solved with an exponential speedup by the famous HHL algorithm, assuming the sparsity. And here also we are assuming the sparsity for the SDP case. So actually, our work is not the first work to give a quantum SDP solver. And I think in the QIP a couple of years ago, Brandon and Swore gave a quantum algorithm with this complexity. So you see that it's basically a quadratic speedup in the number of constraints M and also the dimension N here. And later on, there is a follow-up paper by Van Eppeldoorn et al. That improves the complexity, basically improve the error dependence to be something much better. So here I mentioned that for solving linear system, we have the seminal HHL algorithm that can give exponential speedup. But unfortunately, the same Brandon and Swore paper show a lower bound that basically rule out the possibility of having exponential speedup for solving SDPs by quantum algorithms. That is basically a quantum lower bound here is square root of M plus square root of N. So this is the previous message about quantum SDP solvers. And you might not ask, so here is basically the upper bounds provided by Brandon and Swore and Van Eppeldoorn et al. But the lower bound here is really like we have a gap compared to the upper bound side here. So a very natural question here that people might ask is that, can we close the gap between the upper bound and lower bounds here? So our first contribution is that basically we prove an upper bound that really matches the lower bound. That actually the original lower bound is the correct answer. That is to say, we gave a quantum algorithm that solves SDP with high success probability using this number of quantum gates and queries to oracles. So compared to the classical state of the art, the matrix multiplicative weight framework result, so basically it is this one, we see that basically the quantum algorithm here, we really gave a polynomial speed up in m, n, and gamma. So I think here I probably need to be a little bit more careful because I mentioned this kind of quantum gates and queries to oracles. But what are the oracles here? This basically aligns with previous quantum algorithm literatures, especially for sparse matrices. So here we just call them sparse matrix input model. That is basically we have this two kinds of unitaries. So if we have some indexes on j, k, and I, so basically the first oracle is going to return the element in the matrix AJ, and the element is in the kth row and ith column. And also, we are going to have a unitary that really want to justify the sparsity structure of the corresponding encoding. So that is, if we have indexes j, k, and l, we are going to return a value of sjkl, which is basically the index of the lth non-zero element in the kth row of the matrix AJ. So this is basically a quite common thing that, for instance, used in this HHL paper for semi-linear systems, using a lot of literatures for Hamiltonian simulation, etc. But here it is still a little bit, I would say, somewhat contrived because I think, for instance, in many machine learning and optimization applications, you don't necessarily especially have this kind of sparsity structure here. So maybe one question from the quantum algorithm side is that, how about some alternative models? So I think especially for the problem of SDP, one thing that we can think about is that the normalized PSD matrices are just density matrices in quantum information. So would it be a good idea that we just store this SDP as quantum states, I mean density matrices? So for this talk, we consider a model like this, which we call a quantum state model. So here, basically, we assume that for each constraint matrix AJ, we are going to make the subtraction that is going to be a subtraction of two density matrices, some rho j plus, also some density matrix rho j minus, and up to some normalizing coefficients mu j plus and mu j minus. So these coefficients are non-negative, and we are directly giving the copies of density matrices rho j plus and rho j minus. And we need to somewhat have a promise about whether this composition is good or not. That is basically we want to make sure that the summation of this coefficient that must be for all the constraints j from 1 to m. So having this quantum state model, actually, we indeed can give a better quantum algorithm, which is our second main result. That actually, we have a quantum algorithm with high success probability, only using this number of quantum gates and queries to the quantum state model. So you see here, like the dependence in M, like the number of constraints is square root of M. But the good thing here is that the complexity bound here is irrelevant within, or I should not say, probably it's not irrelevant, but it's only polylogarithmic in N. And the dependence here, we have a B, which is a polynomial in B, also a polynomial in gamma. But the good thing here is that, at least from the explicit form here, we only have a polylog N dependence. Another thing that we introduce in our work is a model called quantum operator model. So here for the quantum operator model, for each constraint matrix AJ here, we are going to assume a unitary UJ, whose upper left corner is actually this constraint matrix AJ, but maybe it's up to some global constant alpha here. So why do you want to study this operator model? I think there are basically two reasons. So the first reason is basically this really aligns with the recent technique, for instance, like the block encoding technique that Anders Gillian introduced in this morning about the singular value transformation techniques. But on the other hand, I think this is just like a mutual generalization of the previous sparse models and also the quantum state models here that we just respectively take alpha equals to S and alpha equals to B in the corresponding two models. And actually for this a model for studying quantum SDP solvers, we also gave a fast quantum algorithm with this complexity, which is just the complexity for the sparse input model, but we replace the corresponding S by this alpha here. Yeah, so that's basically our main result to give a new quantum algorithm for solving SDPs, and we actually find the application of our SDP solvers. That is the problem of efficient learnability of quantum states. So in particular, we studied a problem called shadow tomography proposed by Scott Aronson. That is basically if we're given copies of a density matrix row, also assume that we have some two outcome POVMs, even to EM, we want to prepare a state sigma with efficient representation such that the traces of your state is really close to the truth traces. So in this paper by Scott Aronson, it has shown that the sample complexity of this task is really small. But in addition, our quantum SDP solver really like give an efficient circuit for the problem that basically we can solve the shadow tomography problem with this gate complexity. Yeah, so maybe let me just give a quick recap here because this is basically I just introduced the main results in our work. So basically we gave 3 quantum SDP solvers for various models. So in particular, we have this sparse input model that directly align with the previous quantum algorithm results like survey linear systems, Hamiltonian simulation, etc., which has this complexity and has a polynomial speedup in both M, N, and gamma compared to the classical counterpart. And also we studied this kind of stronger quantum state model where we get copies of density matrices. And the good thing for this algorithm is that the complexity is only polylog in the dimension dependence N. And also we have a quantum operator model that mutually generalizes both input models. That is, and also this model is also interested in general quantum algorithm techniques and also have this complexity here. Sorry. So these are basically the results that we get in this work. And maybe for the rest half my talk, maybe let me briefly discuss about the techniques that is used in this work. So in general, we use an iterative algorithm to solve the SDP problem. So what do I mean by iterative algorithm? So in general, maybe you want to solve a problem where you have a certain function fx, and you also have a constraint set x, p, such that you want to make sure that your x belongs to the feasible set p here. So in general, this iterative algorithm, for instance, if you have t iterations, it is going to work like sequentially that at step I here, you're going to determine your value of xi based on the previous information of xi minus 1 to x1, and also your setting of the problem about the p and the f here. So in general, we are going to use this framework of iterative algorithm to solve the SDP. And in general, we do not directly solve the optimization problem, but instead we make a reduction to the SDP feasibility testing problem. That there is not like for this problem, we have a function that we want to maximize with, but we only consider this kind of inequalities that comes from the SDP problem. We want to make sure whether this set of problems is feasible. If a problem is feasible, that is to say we have a solution for this set of inequalities, and if the problem is not feasible, that is to say the solution set is an empty set. So why do I say that we can solve the feasibility problem by solving the optimization problem by solving the feasibility problem? This is basically because we can make a reduction that to use only like roughly up to polylogarithmic factors, a constant number of queries caused to the feasibility testing problem, because we can actually apply a binary search on the target matrix C here, because we can just regard the matrix C here as another constraint here, as another constraint, matrix constraint here, and basically we can just apply a binary search on the BIs here. So basically throughout my talk, I'm just going to discuss about the feasibility testing problem, and basically this is like this kind of reduction is always taken for the optimization side. So in particular, our iterative algorithm is going to actually use this multiplicative weight method that comes from the classical counterpart. So the algorithm looks like this. So basically, it has quite a few iterations, and we are going to start with a certain weight matrix. And the first start weight matrix is just the identity matrix in the n-dimensional Hilbert space. So at each iteration, we are going to do a few steps. So we are first going to compute a density matrix, which is a normalization of your weight matrix. And next, we are going to observe the gain matrix. And later, I will explain what do I mean by observe a gain matrix here. So next, we are basically going to define the new weight matrix, which is going to be an exponential of the summation of all the previous gain matrices. So specifically, if you want to consider solving SDPs for this using this MMW framework, we're going to do something like this. So basically, you see that at each step, we are going to return a density matrix rho T here, which is just good, which is just like we can directly use as a solution of the SDP maybe. So we just guess this to be a possible solution of the SDP problem. So if we are really lucky that this is indeed a feasible solution, then we are basically good. That is, we find a feasible solution, and we can terminate the algorithm. But maybe on the other hand, we are not that lucky. So if the xt here is not feasible, that is to say, at least for the current SDP problem, there exists at least a well-lit constraint. That is, for this constraint, the trace inequality is not correct, and we call such such a constraint to be a valid constraint, we just take the corresponding gain matrix in the MMW framework to be this valid constraint. And we update accordingly, and we just feed in the current valid constraint to be this MT here, and just here for the new weight matrix, we just take the summation of all the previous, this kind of valid constraint matrices, and we take their exponential. So you see, this basically is like it's some like a dichotomy here. So if either we are good or we are not good, but we are going to know something is well-related, and we are going to fit in the well-related thing in our framework. So this algorithm is like an iterative algorithm, and you might be curious. So what if like the thing is like happening again and again, that each time something is well-related? This indeed can happen. And you might be aware that if like this algorithm is running for too many runs, then it's probably just because your SDP is infeasible. So here we are basically going to set a global upper bound capital here, capital T here, that if the small t here, the number of iterations reaches this threshold, we are just going to cut down the algorithm and tell you that SDP is infeasible. So the good thing from the classical MMW framework is that it turns out that for some SDPs, the number of iterations here is really small. It's something like 16 times log n over epsilon squared surfaces. So in our quantum SDP, so where we directly follow this framework. We didn't improve give like a quantum version for the framework, but actually for our quantum speedup, we improved the execution of each iterations here. So in particular, taking a closer look at each iteration, there are basically two main steps that we need to work with. The first thing is that we basically need to find a valid constraint in the SDP that basically we want to fit in for this gain matrix MT here. And also, on the other hand, a very important step here is that we need to prepare the Gibbs rho t, which is basically the exponential of the summation of some matrices divided by its corresponding trace. I'm going to discuss about these two steps separately. So first, about finding a valid constraint. To find a valid constraint, we provide with a new technique called a fast quantum OR lemma. Actually, I think the quantum OR lemma result is also a previously QIP talk, but our result here is a fast version that is really like a circuit efficient version. So for this problem, we are going, for this lemma, we are going to have a few projectors, and we are also going to have a density matrix rho here. And the traces of this density matrix rho with respect to these projectors are in some sort of OR relationship. That is, either one of the trees is large or the summation of all the traces is small. So basically for this talk, it is known by the previous quantum OR lemma. I think it was by Harold and Montanaro, that basically you can have a test that only using one copy of the density matrix such that you can solve the property testing problem with high success probability. But in addition, we based on their quantum OR lemma, we gave their fast version that we show that this task only requires a roughly square root of m number of quantum operations. And actually, this is the main reason that is why we can decoupling the m and n dependence compared to the very first Brandon and Swar paper and the Van Apeldoorn and Oz paper, that we can really improve the complexity from square root of m times square root of n to the square root of m plus square root of n that actually matches the quantum lower bound here. The second technique we introduce is like a more efficient way to prepare Gibbs states. So the main result is as follows. So if we have a beta larger than 0, where beta is just like a constant for the inverse of the temperature, and here we also have the quantum state model for Hamiltonian H, which is basically written as a subtraction of two density matrices, rho plus and rho minus, then basically we can prepare the Gibbs state e to the minus beta h divided by its trace with error epsilon, and with cost only like a polynomial in beta, and with polylog in the dimension dependence and also the error dependence. So to do this, the idea is that we set a certain threshold for the eigenvalues of H, and we are going to make divisions accordingly. So for the eigenvalues with a large absolute value, we are going to start with the density matrix rho j plus rho minus over 2, and basically we are going to apply some rejection sampling to implement the map e to the minus beta h, and we want to do this to sample from the large eigenvalues. And for the small eigenvalue part, you are going to imagine that this is really going to be very close to the identity that is basically the maximally entangled state here, and still we are going to apply the rejection sampling to implement the corresponding map e to the minus beta h. The only remaining question here is that how we are going to implement the map. And I think there are various ways to implement this map. And I think maybe we can just use, for instance, use the state-of-the-art result, I think, as talked by Anders Gillian's talk this morning, which can basically improve this map e to the minus beta h very efficiently. Yeah, so I think this basically the end of the quantum algorithm side. And maybe let me also briefly discuss about the quantum lower bounds here. So for all the three models, we have some quantum lower bounds. The sparse input model lower bound is not shown by us. It was shown by the very first Brandon and Swar paper. But the good thing here is that our quantum algorithm really matches their lower bound. So secondly, for the quantum state model, we have a lower bound in square root of m times b over epsilon. And for the quantum operator input model, we have a lower bound like square root of m times alpha over epsilon. So that is to say, the square root of m factor is basically necessary, which is basically you imagine that we have some constraints here. This square root of m is just due to the lower bound for Grover's search. But on the other hand, for this lower bound, for the state model, we have a lower bound in B, and for the quantum operator input model, we have a lower bound in alpha. That is to say, the polynomial dependence on the parameters B, alpha, and also like the 1 over epsilon dependence here are at least necessary for, for these models. So this basically quite close to the end of my talk, and maybe let me make some conclusions. A quick recap here is that still that we have the three models that can solve SDPs by quantum algorithm more efficiently, and also we have an application to the problem of learning quantum states that basically we can keep the original sample complexity but give a more efficient quantum circuit for the task. And maybe let me also briefly discuss about the potential open questions along this line. So maybe the first question here is that, are there any other meaningful input models for SDPs? So I'm not sure, like, asking for other kind of input models is like a contract question or not, but I think it's just like, it's very natural that if we really want to get a quantum speed up, it's very natural to think about whether we are considered something reasonable. So for instance, like I recently have a paper with Lin and Wang that we gave a quantum-inspired classical polylogarithmic time algorithm for solving low-rank SDPs via a sampling approach and based on a sample-based framework. That is to say, if you really consider some kind of sample-based model, probably your quantum SDP is not the smartest thing to do. That is really probably quite close to the classical counterpart. So if you really want to have some meaningful quantum SDP solvers, we have to be careful about the input models that we choose for the studying of the problem. And also correspondingly, this raises another natural question that is, can we design more efficient oracles for specific problems? I think here it's just like we are going to give generic SDP solvers for this kind of models, for that kind of models, but maybe for some very interesting specific SDP problem, such models are just so natural that can be efficiently implemented. And we are looking for whether this kind of problems can be found in a short time. And also, I think, like for the design of the quantum algorithm, we have to say that we follow quite closely to the classical MMW framework. That basically we directly use the framework without reducing the number of iterations. This is basically something totally classical. And in general, maybe for some other optimization problems, we are not so lucky that the number of iterations can be something large. And I was wondering if we can still get gain some benefits from the quantum counterpart here. So I think this probably might rely on some classical sequential to parallel algorithm design here, and I think this is probably something valuable that we probably should study next. Yeah, I guess that's basically the end of my talk, and thanks for all of you.
So I'd like to open the floor for questions. Please raise your hand, and the microphone will come around to you.
Oh, there's a question.
So you mentioned that you were considering primarily the feasibility problem of SDPs here.
Yes.
But if you wanted an actual solution to your SDP, what form would that solution be in?
Yes. Oh, that's a very good question. So a very good thing about this MMW framework is that it actually is like a constructive proof. So basically, as I just mentioned in this iterative algorithm, so each time you're basically going to test whether your density matrix is a good solution or not. So if your SDP is feasible, then it has proved that with like the total number of runs to be like 16 times log over epsilon squared, then basically you are after all going to find a feasible solution. And that is to say your the rho t here for the current is feasible, and I'm just going to return this density matrix as an explicit solution here. That is true. The return is a quantum density matrix. But how to utilize that is another story here. You're welcome.
More questions? Good, then I get to ask one.
Sure.
So could you comment a little bit on comparing
the quantum and classical complexity? You gave the two best classical algorithms at the beginning, and your quantum algorithms were all significant speedups over those two algorithms, but those algorithms had very different complexity.
Yes.
So what are the classical bounds? Is it possible that some quantum-inspired classical algorithm could match these quantum bounds?
Let me see. Well, I think I cannot rule out this kind of possibility here. I think for our quantum algorithm here, yes, maybe let's go back to the classical algorithm. Yes. So here, basically, we are quite focusing on the second part, this kind of MMW framework. We are not that careful about the error dependence, but we are careful about the M and N dependence. So actually, you see for our lower bounds that we indeed show like a 1 over epsilon lower bound. So this is kind of absurd compared to the cutting plane method because classically is a polylog error dependence at the first hand. But it's just because like the other part is so small, and actually there are some intrinsic relationship actually between like the dimension and the epsilon here. If epsilon is really going down to some extent, then basically there are some you cannot like directly say that this. I would say this is a little bit tricky here to say. And for the classical inspired thing, I think I like my recent paper and also tracing very back to this kind of Tang's paper. I think the model is just quite different. So there is like a sample-based model where basically you can sample according to the Frobenius norm of these matrices. You can sample according to the Frobenius norm and also like the spectral norm of the rows of the matrix. But here is like something totally different from the quantum models here, which is probably not very easy to make a fair comparison.
Okay. So one final call for questions. In that case, let's thank Tongyang again.